So we're wrapping up our last day of P-Chem here, and it says solid state lasers. What's solid state mean? Yeah, solid. So the lasing medium is a solid, right? We've had our helium neon laser, used it in P-Chem lab. Well, what's the lasing medium in that? Yeah, helium neon gas, right, mixture. Okay. So what's with these multiple levels here? What's going on here? Here's the lasing medium, right? Here's the lasing wavelength for this solid state laser in this picture. Here it is over here. What's with all these electronic states? Remember this? With these lasing systems? I mean, all you need is two, right? You need an excited state and a lower state. Boom, you're done. What's with all these other states they're drawn in there? You had to achieve a what? Population inversion. So I don't really see it here so much, but I definitely see it here. How it's easier to get a population inversion with all these different levels, right? Because there's nothing here in the beginning. So it'd be really easy to achieve a population inversion in a system like that. So we'll talk more about the helium neon laser in with those handouts. I think it's a lot better. Where? Here. What type of laser is this? What do you think? Versus what type of laser is that? Is there a little gas in this laser pointer? What's in here? It's a diode, which is a solid. So this would be a solid state laser, right? Okay, here's another one. I don't know, man. People are different nowadays. To me, when something breaks, the first thing I want to do is just rip it apart because it's broken. You can't do any damage, right? Now you can hurt yourself because it's hot, right? I don't know why it's not on. See, that's why it's torn apart, because it wasn't working so good. Oh, it's not plugged in. That's why. Because I got it working. Just don't touch that, okay? Glorianne, anyone comes near it, just throw yourself on top of it. All right. First, before I flick it on, what is this? You recognize the parts of this thing? Here's like a circuit board. Something fancy's going on here, but what do you think this thing is? Probably easier for you to turn it on. There it goes. So you can kind of see that. All right. Which end's the output? If you can't see, you got to get up. Is it this end? Or is it that end? Which one looks brighter?
That one.
This one. Yeah, this is most definitely the output. So it has the two mirrors on the end. Okay. I don't know if you can. What's probably in there? Does it look like a solid in there? Just a glass tube. This is definitely a gas. This is a helium neon laser. Okay. And I think it's you don't want to be touching anything in there, but it gives you you can kind of see the parts of what we're going to be talking about. Oh, now it's safe. So if you want to take a closer look at it, but so a lot of these different laser diagrams I'm just kind of skipping over. What I think is really interesting though is maybe they meant to do this, maybe they didn't. Here's like our laser pointers, right? Our helium and neon laser that we used in P-Chem lab to make a Michelson interferometer. Then there's some more powerful lasers. Argon ion, carbon dioxide, and do you remember, I don't remember if it's this class or not. I showed a video of a U.S. Navy ship. Did I show you guys this? And then the screen goes down, and this cool looking Star Wars laser contraption goes up, and then the video's on this pickup truck or something. I didn't show you guys this?
No, show us.
What class was that? Yeah, but I can't show it to you if I don't remember what class it was in.
None of us have seen it. Think stuff just make think.
It was the coolest thing I've ever seen on NBC News. Just like Star Wars. And then it cost 50 cents a bullet. Because they're just shooting lasers. It's the coolest dang thing I ever saw. I'll see if now I gotta find the knuckles and I gotta find the lasers thing. I don't remember what. Maybe I haven't shown it to any classes. I just got it. I edited the video and I cut out the junk, and maybe I just haven't incorporated it. Well, I'll look for it. So what I thought was kind of neat was how he had this organized. I don't know if he meant to or not. Here's the powerful lasers. And then, but it's only good for one wavelength. I mean, argon ion laser, whatever that difference in excited states are, or up here, 488 to 514 nanometers. There's several lines that they can pick from, and they can set up their laser cavity, which is kind of like this. Laser cavity are these mirrors that are aligned right, and you can adjust it to pick one of those different lines, but even there, like 3 or 4 lines. Oh, good is that? What if you're trying to study a system that involves some virus and it's taking over all the little goldfish in the world and all the little red ones are dying, and you're trying to figure out what this virus is doing. And this virus is red, and to really study these systems, you want to study it on a time-resolved picosecond system. That's remember what these guys can do? They can send these pulses, right? And so they can excite it, it'll emit light, right? And see how the decay processes, and you can really determine a lot of chemistry on a time-resolved process. I mean, it's not like a movie where, oh, you can see the molecule doing this and this, but if you do enough calculations, you can do that movie with the energy calculations. So time-resolved system is really useful. But my point I'm trying to get at is, well, what good is it if you're only stuck with certain wavelengths? Your system absorbs in this, your analyte or your whatever you're interested in, it absorbs a different wavelength than what your laser's at. Well, that's where this dye laser comes in. And what it is you have one of these really powerful lasers. That's the green one. That's the argon ion laser. That's coming in to a dye laser. And all a dye laser is this really fluorescent dye. There's some compounds where you look at them and, man, they almost look like they're glowing in the dark, this liquid. A lot of those dyes are like that. When you made your bromocresol green or some other bromocresol red solutions in analytical, some of those solutions look really fluorescent. And those strong dyes are highly absorbent, highly emissive. So they make a concentrated solution of it, and they put it in a real syrupy solution like ethylene glycol. And then they have a pump, and it pumps it right in front of that argon ion laser, the really powerful one. So then it emits all these different colors, right? It's a dye. So you can pick different dyes, and it'll emit all this full range of colors. And it's a liquid, so it's a continuous spectrum, right? It's kind of, it's just like this. Right? For a particular dye, that they picked here and in this region, so you can pick whatever wavelength you want, and that's just with this dye. So it's very powerful. So you have a powerful laser coming in, it strikes this kind of really bad picture of a dye stream. So we're talking about a liquid shooting out of a nozzle, and it does look like a rectangle, and then the green laser shoots right through the center. And then it fluoresces all over the place. So it's really inefficient because the only light it's collecting and getting to resonate is what strikes those two mirrors. Okay. But I found this movie with these grad students playing around in lab, and it kind of gives you an idea of a dye laser. Whoop, I gotta, you can even hear them dinking around. I wish I would have made little videos like this when I was playing around in lab. 'Cause these are multi-million-dollar systems that these guys are playing around with. That's just a power meter, 158 milliwatts. Coherent is the name of the company. That's the dye laser, the dye shooting through there. So you can kind of see it's red, so that's the laser that's actually coming from the dye laser. And then shooting into it is a green argon ion laser. Here's the really powerful one that's shooting into it. And then see how it changed color over here? Because that's the dye laser output. So this is the output that they're using in their experiments.
Wow.
See, and their boss would get really, really teed off if he saw this. Do you know why? Because those lasers are really powerful. And chalk dust, I mean smoke, anything, once it gets a little film on the mirrors, it bakes. It's really bad for it. And if you're always doing research, that means you're always on the borderline trying to figure things out. So you need the most power, you need things working the best, and just by treating your equipment that way isn't the best. So that's that. Okay. So that's what's kind of going on here. And then they just kind of select their wavelength they're interested in. And what's also really interesting, I think, is that there's crystals out there where if you needed this is 488 nanometers. What if you needed if you wanted twice the energy, would that be 890 nanometers or 244? Which way are you going if you want more energy? 244. So they call it frequency. I used one. It's a frequency. You remember the name? It's a crystal that doubles the frequency. I forget the exact name of it. It's a crystal that doubles the frequency. So you had this like infrared laser coming in, and it doubles the frequency. So now it's red, and then that went into the dye laser. That's the system that we were messing around with. But so a lot of this stuff, I think, just from the reading is good.
Don't worry about it. Don't worry about it.
You read it. You read it in the book.
Yeah.
Okay. So these schematics, I think, pick out more of the general ideas, which I wish they would have hit on more. And so this is the handout. So So in the handout, they talk, I'm trying to get you to see what a base, where it's kind of goes from beginning to end here. In this first one, here's the output, the laser output. But you're always going to have, in building these lasers, what do they all have in common? They all have their mirrors, right? And then inside is the amplifying medium. So there's something that's doing the lasing action, right? Something that has these electronic states where you can achieve that population inversion and build some stimulated emission, okay? But this whole, this is when you hear the word resonator or cavity, that's this idea. Mirrors surrounding a lasing medium. One of those mirrors is partially, right, partially reflective. They have to be really reflective, those mirrors, but one of them needs to be 100% and the other one less. But, and that's what the book always says, but when we play around with this helium neon laser, those 100% reflective mirrors, I think, are bloody expensive, right? Because you can't build things if you don't make money. So when we saw that, there's a good amount of light coming from each end. They really didn't care, right? Because the output needs to be so many milliwatts if you're going to sell it, and if you're losing some on the back end, it's not 100% reflective. They don't care. It's cost prohibitive for them. They make more money if they put a partially reflective. But one of those needs to be let out a lot of light, though, like 20, 30%. And we saw that. This end was a lot brighter than this end. But the books very often are saying 100% reflective on one end, and you can see in practicality that's not exactly the case. But there's, do you remember the slinky, right? And then Gloriana or someone was holding one end, and then I was doing this on one end. Okay, I was building what waves? Started with an S.
Sinusoidal.
Yeah, they're sinusoidal. ST. Sinusoidal standing waves, right? But they're building standing waves. And so this is how they're depicting them. They're depicting them. And remember, when I did these standing waves, I could generate different standing waves, right? But so there's standing waves are just like, you know, they're energy. You can have lower, they call it more efficient standing waves than others when you talk about these different modes of lasing action, because simply, I think, because of diffraction, you're losing energy. So this is the most stable one. We call it the TEM00. Okay, and we'll see what it looks like. But this is in the inside the cavity. That's what the standing wave looks like. What do you think these lines are? What are they trying to represent? Probably, what does light consist of? Electromagnetic radiation, which consists of
Electricity and magnet.
yeah, electric fields and magnetic fields. And since this is electronic states, this is electronic transitions, they're probably more interested in drawing the what field? Electric field. Yeah, so they're just standing waves of the electric fields, how they're representing it, how it's more intense, less intense, more intense, spread in that sense. So the mirrors on the end, right? El cheapo plane parallel. I think these look very, for this helium neon laser, right? Everything is machined. They just slap them on the end, glue them, they're done, right? So I'm sure they're plane parallel mirrors. But if you're going to be doing research and you need to be like those grad students, every single one of their mirrors are concave. Why? Because, do you remember anything about lenses? They had a what? Focus. They had a focal point, right? So it makes it so much easier to align. And I'm glad that you guys did the Michelson interferometer, because you have some appreciation for trying to align optics. It's frustrating. Or trying to align that corn syrup experiment, right? It can get really frustrating. So by having these concave mirrors, and you're not, and if things get totally off, you can literally pull out the ruler and set things to their confocal length, right, their focal length. If you take a look at the output of these lasers, now it doesn't matter whether we're talking about the laser, like a dye laser or a laser pointer or a argon ion laser or the laser that's shooting out of that laser cannon from the Navy ship that I'm going to look for a video for. There's different modes. There's different standing waves that can be occurring in that laser cavity, and they like the 001. It's the most efficient, and I'm sure that's the most powerful. I'm sure that's what that laser gun is doing. Okay. Let's see. I think now we're focusing in on that helium neon laser a little bit more. All right. So I think this is the other page of the handout. Yeah. Do you remember, let's jump down to here quick. Remember we heard solid state laser? Here's an example of how you can get a solid state laser. Okay. You literally have a rod made of the material, right? Like crystalline. Oh, give some examples. Ruby, I forget what they're doped with, but they make these rods of this material, right? And then somehow you need to excite them, develop this population inversion. Hopefully it's a 4-level laser, it'll be a lot easier to achieve. But see how they call it a flash lamp, and it's just wrapped around it. How can you make a lamp like that? Don't lamps have a little prong here, a little prong here, a little filament that goes in between? How can you make a flash lamp that actually wraps around a tube like that? Or did they mislabel it? Can you make lights like that? It would have to be a gas. You take those discharge tubes, right? And if you heat them up, you can bend them in whatever shape you want. And that's all they did. And flash lamps, so they're igniting them, but pulsing them, or lighting them, turning them off, lighting them, turning them off, lighting them, turning them off. Okay. So, or you could have a straight one like this one. I guess it would be a lot cheaper, right? And then surround the whole thing with a mirror or something. Okay. So if you're wondering how they built some of those things, that's one way. They call these Brewster windows because usually you get reflectance, right? If you have a window here and you want light to go out, well, you get light reflecting back at you. But if you're at the Brewster angle, 100% of the light of a certain polarity just goes straight through. There's no reflectance at all. And there's real advantages to that because then your light your output's polarized too. So, but this isn't how our helium neon laser is, I don't think. I mean, it's just got those. I don't know, I don't think so. I can't see any Brewster windows in there. I don't think they really cared. So I think all of this was how they're building up that population inversion. And how in a helium neon laser, you can actually pick different lasing wavelengths, right? What's the little mu? Mu is a Greek symbol for... Yeah, but for a length, it's a unit of Micron, 10 to the negative 6. Now, is that long or short in comparison to like these nanometers that we had before? Or colors? Colors are what? Nanometers. Which one's longer? This one, definitely. So this is IR. And I'm pretty sure that's what that Navy one is, but I'm not so sure. Okay. Because you didn't see anything. But it could be just a really high energy pulse, and there's no way you're going to see it. But I think, we're just talking about 632 nanometers, so that's the one that we're picking. I don't know, is there anything I really want to get out of this? No, I just thought the handout was kind of neat. Gave you a little more insights. It's the same thing twice, isn't it? Well, it's the same thing twice. Weird. All right. So that's about really all I have. So you can get your homework done.